All right, so this is Team 13. I'm Noah Sanford,
I'm Ethan Hewlin.
And I'm Austin Novelli.
and our project is calculating the spanning modulus of a graph.
So just kind of give you all a general overview. So the program calculates the modulus of a spanning tree when given a set of edges for said tree. It was created by Dr. Nathan Albin and Pietro Pochi here at K-State. It was written in C++ and uses the Boost library primarily. So just to give some more background, so what is a spanning modulus? Basically, it sets of edges on a graph, tying together a bunch of different concepts. We're going to go into those in a little bit. Those are outlined here down below. Cunningham's algorithm, which is made up of the rank, the polymatroid, the greedy algorithm, and the max flow. We'll go into that in a bit. Here's those concepts that we're going to go over. So the rank of the graph is determined by the large set of edges that don't form a cycle. So here, you take a look at this picture on the left, you have all of the components, but none of them are connected for that first one, the top left. Therefore, the rank is 0. You have 5 components. One side of them are connected. Therefore, the rank is so 5 minus 4. Therefore, the rank is 1, and we just keep going on from there. And it's also equal to the rank of the adjacency matrix of the graph. Just to summarize what exactly a polymatroid is, it's basically just a non-negative vector indexed by set E. It's defined by some non-negative vectors such that every subset is less than or equal to another, less than or equal to the whole. And all these equations and inequalities here kind of make sure that everything is valid. And here, Cunningham's algorithm, that's used to find the vulnerable set of edges in a graph. So here on the right, we're going through a bunch of different ones here, kind of outlining what exactly falls into our criteria. So the smallest ratio here is where the graph holds vulnerability. And it goes through all of the possible ranks over the total edges. From smallest to largest, and computes if x of v is greater than or equal to q of the absolute v minus 1. And if you take a look at the chart, it kind of outlines that as well.
And then this chart is also the list that the program does a binary search through to find a specific graph vulnerability, but we'll get into that a little bit later. So for some related work, for the actual spanning tree modulus algorithm itself, there isn't any real related work on that algorithm because it was created by Dr. Albin and Pietro Poggi-Corradini. The algorithm uses some of the concepts that we just discussed, like rank. It also uses Cunningham's algorithm, and even inside of that, there's a max flow and greedy algorithm that are used, but those are both done through a library call. So they're not actually coded in. It's just using like the library's math concept implementation. So some of the other related work that isn't related to the actual algorithm and is related to problems that we'll need to solve. One is max flow. So the algorithm spends quite a bit of time doing max flow calculations on the graphs and the subgraphs. So there are parallel max flow algorithms that we can take inspiration from if we wanted to code our own instead of using the Boost library call. But there also is a Boost parallel graph library that may have some parallel max flow functions that we can try out and compare, one, to the version that's already there, and two, to any manually coded versions that we create. Another problem with some related work is a binary search. Parallel binary searches do exist, but they're fairly complicated and don't really apply to the kind of binary search that we're doing. And we'll talk about that a bit more later in our implementation section. So the existing code currently exists as a C++ file and a set of header files that utilize the Boost library for some graph functions like creating graph objects and applying some standard graph operations to them. And then the main meat of the program is contained within that modulus function, which then has a series of other nested function calls to do Cunningham's algorithm and a max flow and all the stuff that lets the algorithm go. And then there's also a dummy Python script that we've been referencing that's a bit more cleaned up than the C++ file to find some good areas for parallelization. So to break down the code here, the code is a series of nested loops. So there's an outer while loop that serves as a queue for the edges that need to be processed. And as edges are processed, the program can find more edges that need to be processed and need to have their vulnerability value and things calculated. So as an edge is processed, it can actually add edges to the queue, which means it's a pretty good target for parallelization. And we'll get into that a little bit later. The inner while loop does a binary search on the set of edges that it's given through the modulus function, and then searches for a specific graph vulnerability value. And then once it finds that value, it does some more calculations that end up calling the inner while loop, which performs a max flow calculation on the edges from the previous loop to get the critical set, which it can then use to calculate the modulus and return all the way back out to the outer layer. And then once the program is done, it computes the modulus for the spanning tree and prints it out along with the number of edges in that modulus set, as well as the number of edges and components remaining that aren't in that set. So it actually runs through several iterations based on like an edges graph vulnerability value. So that chart at the bottom is what the program outputs. So for the vulnerability value or the modulus of 1/2, there are 20 edges in it. 85 edges are not or do not have a modulus of 1/2, and then there are 11 connected components or that don't have a modulus of 1/2. And that graph up in the top right there is kind of showing that. So the first row is the set of edges and points in the outer layer there that are colored gray. And then the second row is that inner layer that's colored orange. And the third row is that inner layer that's colored green. So it iterates through all the edges, and as it processes them, it finds different moduluses for them and spits out the output like that. So our plan to analyze the performance is that we're going to augment the program to record how long each call to that modulus function takes and measure it in milliseconds. Then we're going to gather runtimes for each of the 4 different data sets that Dr. Albin provided us. There's 4 that he gave us that range from super simple, it takes like 5 milliseconds to run it, to really complicated. We did a test run and it took more than 2 hours before Beocat kicked our job out. So that one is definitely very complicated. And then we're also going to run our parallel program at multiple thread counts for each of those 4 data sets. We're going to do it at 2, 4, 8, and 16 threads, since this will likely be run on Dr. Albin's computer or somebody's personal machine. And then we'll also test it at 20 threads on Beocat just to see how fast we can get the program to actually run. And then we'll compare the serial version's performance to the parallel version and at the different thread counts and at the different data sets to see if our performance is improving and see what might be causing the improvements. And then we're also going to compare the different thread counts to each other in case there's any added overhead and determine what the most effective thread count, if there is one, and if there is, have the program run at that or fewer threads. And then to verify our results and make sure that the program is actually working correctly, the program has a deterministic outcome. So if you feed it a graph and a set of edges, it's going to produce the same output every single time. So whenever we parallelize the program, we just need to make sure that it's producing that exact same output on each of the 4 data sets. We're also going to work with Dr. Albin to make sure that any math code changes that we make are correct. as far as the algorithm goes. So for example, if we end up coding our own max flow algorithm, we'll check with him to make sure that we're doing the algorithm correctly and that we don't have like a math understanding gap that causes error. There is one exception for it producing the same results every time. The program can sometimes say that all of the nodes in the graph make up the critical set, which causes the modulus function to get thrown off and you don't get good data. However, according to Dr. Albin, this doesn't happen ever really. He said he's never seen it happen, but the code is augmented to handle it. If it does, it'll recognize that it basically just returned the entire graph and rerun it, and it prints an error message out. So if we get that error message, we'll know to throw away that run and rerun it again at whatever conditions we were using.
Yeah, so for the way we're actually going to parallelize and approach this problem, there's the kind of standard OMP, pthreads, MPI. We're going to go with OpenMP since it's easy to implement. We have a bit more experience with it, and it's just you throw in some comments and it makes it parallel. I mean, it's really easy to work with, and then that we're not going to be targeting distributed computing, so we're not going to deal with kind of the complexity and overhead that MPI would introduce if we wanted to push it to unlimited scaling. And then as far as where we're going to target, there were several parts of the code that were highlighted by Dr. Albin when we met with him. And then kind of in order of priority of how we're going to attack them, there is a task queue that builds up itself as it's executing itself. So at the end of a run of that queue, it adds more to the queue, and then it just loops through that queue until it completes. There's a max flow calculation, as we have discussed. There's kind of just random miscellaneous loops that we can try to parallelize if we get to that. And then there's Dr. Albin did suggest the binary search as a target for parallelization, which for reasons we'll discuss later, we're not going to pursue. The task queue itself, this is that top level loop that Noah had been discussing earlier. So this, it has those multiple sets underneath it. So if we can effectively parallelize here, we can kind of get the benefit of parallelization through like the entire program. So we're not, serializing and then parallelizing it, and we can kind of spread everything out just from the very top, which would be, we predict that would be kind of the best approach. So that's where we're going to kind of set as our primary goal, and then the others will be stretch goals if we push on to them. So it is a queue, but we should be able to, and our plan is to replace the queue with a sequence of recursive calls. So as I mentioned before, it's at the end of each, when it completes a task in the queue, it generates a set of items that it adds back onto the queue. So our approach is going to be, instead of adding them back onto the queue, it's just going to do a parallel for loop and call itself on that set of data. And then you'll end up getting less and less items returned as you kind of progress through the algorithm. So you'll end up, branching out, and then it'll come back in as you have fewer and fewer items to execute. And this is probably so the code itself will stay basically the same. It'll just be a kind of a single place that we replace, pushing, popping with that recursive approach. The output would need to be deferred till later. and then sorted, rather than outputting as you kind of complete one chunk of the algorithm, which is how it works right now. Since it is serial, you can finish a single chunk and then spit it out to the output. So instead, we're going to just place that into some sort of shared buffer. And then at the end, after everything's completed, we will retrieve that buffer, sort it, and spit it out to an output folder. But yeah, it is probably going to be our best approach, and we'll start kind of in a single thread and then just grow and grow and grow, and then reduce once it kind of reaches that critical point. The other place we can attack is the max flow calculation. Right now, we're using the Boost library to do a push relabel max flow calculation. There are parallel max flow algorithms that exist. They're not particularly easy because max flow is very connected to itself. But they do exist. We can look into implementing one if our approach for the task queue doesn't yield the acceptable results. Because if the task queue ends up working, then parallelizing farther down the line isn't necessarily going to produce much benefit. But if that doesn't end up panning out, we'll take a look into this. There's also libraries that exist. I have had trouble finding a parallel version within the Boost parallel library for max flow. I found some other libraries, but that would require refactoring a lot of code, since the data structures it's working with are the Boost data structures. And of course, there's always a by hand, which will be a lot more difficult and a lot more labor intense. But if that's what we need to do, we can look into that. And then there's, if kind of the previous two options don't do anything, or if we kind of end up at a lower level of parallelization, what we can do is also look at just kind of miscellaneous for loops. So like in serial parts of the code, if we end up with a deeper down that stack of loops, if that's where we end up having to parallelize, then there will be multiple sections of serial code that we can look into parallelizing. And they're just kind of the generic for loops, just kind of sprinkled throughout, iterating through the graph, which if the graph is large enough, then we would see some benefit, but that would need more testing if we end up needing to approach that. And then the binary search was something that Dr. Albin suggested we look into. From what the research that we did, parallel binary search is used when you have a set of data to search for within a given search space. So you have like 5 elements that you want to find in a search space, which is super easily parallelized, but that's not what we're doing. We're searching for a single item within this data set, which is just not parallelizable. We would end up scaling up the amount of work we do without seeing any sort of reduction in the amount of time it takes to find it. So, and because the plan right now is to parallelize at a level above it, that would end up parallelizing it anyway. But basically we ended up deciding that this is just not an approach we want to pursue. And it seems like our time would be better spent elsewhere.
And I will add that we may not need to do, or the program itself, after looking at it, there may be like potential to switch it to a different kind of search and see if that would be parallelizable. But again, we'll be attempting to parallelize a level above. So that's kind of our super last case, last resort scenario, where if we can't get any other parallelization to stick, we could, rewrite like half the code and make it parallel. But as Austin said, it's kind of hopefully we'll be able to get something above that to stick first. But we have a plan for if nothing else works.
Yeah. And it's a binary search, which is, good runtime anyway, good scalability.
Right.
So. Okay.